Hello and welcome to Quadcast. This is your host Tim.
I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to them. So without further ado, let's get to it. So I guess since it's Halloween, we thought it would be a great idea to have a spooktacular episode or a spooky episode on ghost particles. So I guess let's start off by Tim. I'll pose this question to you. Do you believe in ghosts?
Well, I guess depends on what you mean. I think the regular ghosts that people talk about probably don't exist in that way. But do I believe that there exists some ghostly looking thing in the universe? Yeah, probably. And there are such things in particle physics.
Yeah. Mikey, same question to you as well. Do you believe in ghosts?
Uh, mm, not really.
Are very succinct as usual. So I guess is there anything that comes close to a notion of a ghost? Mikey, I'm just gonna pose this off to you. Just you look eager.
Yeah, there's particles that, pass through you. I, yeah, I guess that's the topic today, right?
Yeah. Tim, how about yourself?
I would say to quantify as a ghost, first of all, it needs to exist. Yeah. And second of all, it
Mhm.
needs to have some energy, hopefully, so that its existence is meaningful. And thirdly, it can't just do nothing, right? Like the only reason ghost stories are interesting is because something spooky happens. So I think the right candidate for finding ghosts in particle physics would be something that is, you know, that is kind of spooky, but also it has some interesting phenomenon.
Huh. So I guess so it has to, okay, so to go over your criterion, it needs to exist, and by exist you mean it needs to have some energy. It needs to do something. It just can't be existing but not really interacting with us.
Yeah, but
And so those
it can't do something all the time. Like unlike electrons and protons, because we see it. If we see it every day, then it's not
yeah.
spooky anymore. So it has to be that we see it occasionally enough that it becomes spooky. I think.
Oh, okay, so what you're defining is a spooky ghost, not necessarily a ghost.
Yeah, I think so, and that's
Okay,
necessary.
okay, okay. I guess we've talked in the previous episodes about dark matter, and for folks that are tuning in, this is one of the first episodes of our of seeing us. We've had previous episodes talking about dark matter, dark energy, and whatnot. So I'll just summarize here and say that dark matter doesn't interact very much. I mean, it's very weakly interacting, or at least that's the hypothesis behind it. Would you consider that to be a ghost, Tim?
Yeah, I would say it has some properties of a ghost, but
Mm.
but the thing is, it never spook us because if it had, we would have seen the Nobel Prize getting awarded to the discovery of dark matter.
Uh-huh.
So it's not quite there yet. I would say it's a little too dark to be a ghost. I think.
So I see. So you're saying because it doesn't interact enough, it doesn't really do anything. It's not really scary in some sense. It doesn't really scare us very
I think
much.
so. I think it's got to be scary, especially for Halloween.
Mm.
So
What
what
about
particle is scary, Tim?
Huh?
What particle does scare you?
keeps you up at night?
I mean, probably not the particle that we'll be talking about, but I think in a spooky way, probably the particles that we'll be talking about. I think that one fits the bill.
Mhm. Makes Makes sense. So I guess like let's jump to it and talk about the particle that we're going to talk about, the most spectacular particle agreed upon by us three. So Tim, I would like you to actually Mikey, if you do a drum roll, and Tim, you can go and announce the particle.
Oh, drum roll?
Yeah, drum roll, drum roll.
Okay.
I don't think Zoom can do simultaneous sounds, but I'll take that.
Okay.
Yeah.
All right,
Well,
assume a drum roll has been given. What is this most spectacular particle, Tim?
yeah, and I would say these if you Google just ghostly particles, it turns out that the one that shows up, all over the pages, that these are particles called neutrinos. And
Mhm.
and some of us might, some of the listeners might not be familiar with it, but it turns out that the sun makes a lot of neutrinos. Radioactive decay makes neutrinos. Fusion reaction makes neutrinos. And the beginning of the universe also makes neutrinos. And in fact, if you look at the numbers, just the size of your thumb, every second they are close to 100 billion neutrinos passing through you right now. So it's kind of a spooky particle, and we have observed these ghostly beings coming from the sun. So neutrinos
Gotcha, gotcha. This is interesting. 100 billion through my thumb, and you said 1 second, right?
every second. Yes.
Oh wow, that's interesting. Mikey, could you lay some groundwork of what is a neutrino to someone who like doesn't know, only knows like electrons and protons? What how would I
Um,
be able to relate to neutrinos?
how do you relate to a neutrino?
Yeah.
We- how do we relate to a neutrino? I mean, we don't really.
I guess okay, then how would you explain a neutrino to somebody who has like taken high school physics, for instance, just like understands basic chemistry and whatnot?
Uh, it's a particle that travels close to the speed of light, doesn't interact with ordinary matter, and
I would say in terms of particle physics, neutrino is a close friend to electrons. That's
Mhm.
like the closest thing, but it's not close at all, right? So electrons, as we know, form the basis of chemistry. These are the things that orbit around protons and neutrons, the nuclei. Um, but but neutrinos, because they don't have charge, they are unable to form any atoms, right? So as a
Mhm.
result, when we make a neutrinos, the best they can do is just fly right through it, more or less, because it does not have charge. It just happens, do not have that. So yeah, so the closest thing is the electron, but otherwise, it's a particle that, for a variety of reasons, that most people wouldn't be very familiar with.
Mhm. Is there any history like okay, so if they don't have any charge, that means you can't really like see them per se because we can only see things that emit photons or interact with photons. So how do you even know that these things exist? Like how do I know this is just not one of those like ghost stories around the campfire that just like kind of lore and like tales that may not be substantiated?
Right. So that's where it gets interesting. So you're right that neutrinos don't have charge, so that's why we can't visually see it. So even though they're like, I don't know, 100 billion of them passing through my thumb right now. I mean, if you see it, it will be truly, I guess, spectacular. It wouldn't be spooky anymore. But as you can imagine, that's a lot of neutrinos, right? 100 billion. Can you imagine
Mhm.
like through your house how many billion there will be passing through your house, right? So it turns out that neutrinos, even though they don't interact with us electromagnetically, they come from radioactive decay, right? And because of that, it means that they actually has weak interactions. Yeah. So these weak interactions are very, very rare, which which is what makes them spooky. But if you have a material that's dense enough and you have a lot of it and you wait long enough, it turns out that those neutrinos will pretty consistently kind of leave an imprint I guess kind of their spooky way of saying hi occasionally.
Yeah, can we elucidate further what weak interactions means? Because I think of weak interactions, I think of like interactions that are not as strong or like just kind of very feeble interactions. But I'm assuming that's not what you meant. You
Uh,
give a very like one sentence or two sentence explanation of what a weak interaction is.
yeah, weak interaction. The reason it's weak is because the things that weak interaction does is very rare. But
Mm,
the crux of the weak interaction is that interactions involve particles changing species. Yeah. So if you have a
mm,
radioactive decay, a proton can change into a neutron, but that comes at a cost. In order for that to happen, some other particle has to be spit out. For example, there's an electron and an antineutrino that got spit out. And that's usually kind of overlooked when people study physics. But it is required for these extra particles to come out in order for the interaction to happen. And as a result, you can generally imagine that the weak interaction allows a species to change. For example, a neutrino can come in. If it has enough energy, it can convert spontaneously into an electron back. It can kind of come poof into existence, sort of.
mhm.
Or occasionally, well, the weak interaction also doesn't necessarily have to change species. So it's not a requirement, but it could. But occasionally it could also knock off other particles. It could knock an electron out. So, for instance, sometimes it could hit, for example, the memory in your computer and cause an error. Maybe that could explain why some Windows computer keep crashing and whatnot. But probably not. But it could happen.
I see. Is that less likely than like radiation from the sun? Because I remember there have been very specific instances of like computer memory or chips getting like changing a bit from a 0 to 1 and that changing certain computations. Like there's probably some election result that got like got tweaked due to like a bit flipping from a 0 to a 1, so some candidate won, had more votes than like the number of like citizens in that particular area. So is that change in computer systems, is it less frequent that a neutrino would change it more than like a photon, for instance, from the
Well,
sun or
well,
similar
you
to
have to
it?
understand
Mm,
neutrino, because the fact that it's neutral sort of gives it a little bit of a superpower. So if you look at
oh.
light, if you look at light, for example, or
Mm,
typical cosmic rays like protons and electron or photon, these
mhm,
have charge, so I can reasonably shield them. Yeah. So if I have a piece of metal, generally
mhm,
it's good enough to shield a lot of these particles. Of course, there will still be some that passes through. Yeah. But with
mhm,
sufficient shielding, those can somewhat be eliminated. But neutrinos, on the other hand, they could pass through the entire Earth without much problem. And of course, the fact that they pass through the Earth so readily also means that they usually don't they usually don't mess things up too much because it's really
mhm.
rare. But remember, there are 100 billion of them going through your thumb every second. I don't care how
Wow.
rare it is, it does happen because there's just so much of it. Yeah.
Are there more neutrinos than like number of photons? Is there even a comparison or like because photons is something that I understand coming from the sun.
Yeah,
It's probably like a lot.
it's a little bit hard to count because the thing is because photons have mass. Sorry, photons do not have mass. So to some extent, you can have like as many photons as possible. So it's not really that easy to count the number of photons. Although some
Mm,
arguments can be made. I guess you could count it. But probably yeah, there are probably more photons coming from the sun. But like most of them get shielded. If you close your blinds, shut all the things from your house, you can kind of shield most of the
mm,
light away.
mm.
But
So
neutrinos, you can't do that. You can't stop neutrinos.
mm, is this due to the fact that like photons interact with charged matter, for lack of better words, and so all the things you would use to shield are made up of like electrons and protons, which are obviously charged. And so when photons come in, they get absorbed, or something happens, they interact with like whatever material you're using to shield yourself. But because neutrinos don't really interact, and they're also neutral, and they don't interact with anything charged, and they mostly pass through things, that's why, like, no matter how much you shield yourself, it won't really do anything.
Yeah, basically, you can't really shield it. Even if you have another planet in front of you, it still will happily pass through it.
I see. So we have a question from the audience asking, what is the mass of neutrino and what speed do they travel at?
Ah, that's a good question. We actually don't know what the mass of neutrino is. We only know that they are very, very small, but not zero. They're very, very, very small. Probably 1,000 times lighter than a typical electron, I think. Somewhere around that ballpark.
We know the relative masses though, right?
Yeah, we know a very we can go into that later. There are actually 3 types of neutrino. They all have some mass, but we know the mass difference between them, but we don't know the absolute mass. We have some idea what they are. They're very small, and in any case, the smallest of those masses means that most of the time they travel so close to the speed of light. You might as well say that they travel at the speed of light for practical purposes.
What one question I have is, how do we know that they have mass? Like, I mean, what's to stop you from just saying they don't have mass? Like, what tells you that they have mass?
Now that's the interesting bit. It turns out that there's a very spooky phenomenon for neutrinos, and that's a discovery for the Nobel Prize, related to the Nobel Prize 2015. The discovery, the fact that they have mass, comes down to this phenomenon, and at first glance, it seems like so unrelated. Seems like completely unrelated to whether they have mass or not. It turns out that neutrinos, there are 3 types of them, they can spontaneously convert from one to the other. And that's the reason why we know that neutrinos definitely have mass, even though they're very, very small.
That seems almost unrelated. How do you even relate those things together? Like, I mean, aren't there other particles that are massless that can do that, or is that a property of having mass?
I think particles without mass definitively do not, or, well, they do not do that in that way. Yeah. Like the thing is, the way neutrinos, so there are 3 types, and we can enumerate them. They are the electron neutrino, they are the muon neutrino, and they are the tau neutrinos, 3 types. And the thing is, the ratio of how much of each actually depends on how much they travel in space and time. Yeah. And the only way to explain it is through quantum physics, because quantum physics says that depending on how much energy a particle has, their wavelength changes. And from Einstein, mass is energy. So the only way, for at least for one beam of neutrino, which more or less has the same energy, in order for them to have this oscillatory behavior, has to be that somehow their mass is somewhat different, right? So that they have slightly different frequencies. So it's almost like playing a guitar chord. You have different notes, so that you hear like a what do you call it? Like a chord. Like a neutrino beam is a chord made up of neutrinos with different beats, right? So that gives rise to different mixture of neutrinos depending on how you're listening to it.
So does that mean you're gonna create a music album of neutrinos, Tim, and go platinum?
Well, I think technically physicists probably have
superstar.
have already created a lot of, I don't know how nice those sound. They already have, technically, I guess, musical output from these neutrinos. And physicists have studied these phenomenon from the sun, from
Mm.
particle physics accelerators, to really look at how these music neutrino notes beat, as a function of distance.
Uh-huh.
And they have found
Yeah.
some interesting stuff. There were mysteries in these results.
Have people seen neutrino oscillations in
Ah.
accelerators?
Oh, I mean, I don't mean accelerator. I mean they use accelerator
I remember
to create
something about
neutrino
it, but
source. I mean they use accelerator to create neutrino beams, and then study it really far away, like a few
oh,
100 kilometers away, to study what comes out. So
right.
Mm.
Oh, yeah, okay.
Yeah.
Yeah, I remember now.
Yeah. So actually, there's an audience question that about something that you mentioned, Tim, but I actually want to pose this to Mikey to hear his perspective on this. Um, so one of the questions is they have a small mass, travel at a high speed, and there are a billion passing through my thumb or 100 billion, and you can't really feel them. Like, is it really that weak? Is I think what the audience member is trying to ask.
oh yeah, it's tiny. It's tiny because I know 100 billion sounds like a fantastical numbers, but just look at like how many atoms are in like.
Yeah, sorry, my internet keeps cutting out, so I dropped off before. Can you say that? Yeah, there's a billion passing through, and what?
Yeah, why do we not
There's a
feel
billion passing through. Oh, go ahead, Tim.
My earphone's not
Yeah,
working.
why do we not feel them going? Oh, can you hear us?
Yeah,
Yeah,
All right, Tim. I'm gonna pose this
are
question
you
to
frozen?
you.
yeah. I think Mikey's
Okay.
having.
Go, Tim.
Yeah, that's okay. Mikey's having some
But Mikey,
technical
it's hard to
difficulty.
hear you. We'll we'll pose this question to
Oh,
you,
for
Tim.
real?
Go.
Okay.
Yeah, yeah. I mean, yeah. 100 billion sounds like a large number, but it really is small compared to like the number of atoms that are in that are just in your thumb, right? That's way more. And each of these, it's like 10 to the 26 or something, right? It's like a billion, something like that. Um,
Yeah.
and each electron, remember, is thousands of times heavier than a neutrino. So yeah, so even though neutrinos do have some mass, they are insignificant. But although in the early universe, it actually affects the expansion rate of the universe because of neutrinos. So we can also measure that, and that's also another hint that neutrinos have to have some mass, because without that mass, the expansion rate of the universe in the beginning will be changed, because there was so much neutrinos when the universe has just begun. So yes, collectively, if you really have a lot of them, they do affect. They you can feel their gravity. You could, but 100 billion is still, it's tiny. But actually, there's another fact. I think there was a little bit of mystery for stars, like the way they shine or whatever. There was some inconsistency that I forgot, but it turns out that stars lose energy as they shine. Neutrinos leave, so that's how they lose energy. Otherwise, if without neutrinos, you can argue that, sure, things come out from the sun, but wouldn't the gravity just pull them back in? So why would the star lose mass? Yeah, you can argue that. But one of the mechanisms for them to do that is through neutrinos. It just flies right through the sun, and that's one way for stars to cool slowly. It's from radiation and also neutrinos getting spit out, and that's very important. Otherwise, all the calculations for stars will get messed up. So you do need neutrinos.
So Tim, if I wanted to generate neutrinos, like, how would I go about that? Like, yeah, what do I need?
You need some kind of decay. That's it. So because neutrino has no charge, it interacts with us predominantly through the weak force. So just grab something that decays. But it doesn't create neutrinos all the time. But I think a lot of things that decay can and do produce neutrinos.
Yeah, you just need a
Mm.
neutron, right?
Yeah, a neutron decay to neutrino. You find some neutrinos. Yes.
Oh,
Yeah, just find a neutron, and then you'll get a neutrino eventually.
all right. That's fair. So we have another audience question. Maybe it might be helpful to break as much as possible. Explain to the audience what this question is actually asking, and then we can answer it. Is the neutrino mass actually a probability of three masses? Is that probability similar to the probability of an electron spin up or down, or the probability of finding a photon in XY polarization?
It's a good analogy, actually. I think so. What do you think, Mikey? I think it's
Sounds right. Yeah. Yeah.
yeah.
How to explain that?
Yeah, it's not bad. And because it is indeed a quantum mechanical effect. The thing is, because because neutrino has so little interactions, when a neutrino gets produced, it is in what we call quantum mechanical superposition. It could be one of the three types, depending on how it's produced. And for example, if let's say a neutron decay, I think you would find a neutrino, I think, because a neutron decay into a proton and an electron.
I thought it was an anti-neutrino.
Oh yeah, sorry, an anti-neutrino. You find an anti-neutrino, yeah. But then this anti-neutrino, because it doesn't interact very much, it maintains this quantum mechanical property. So because it hasn't bumped into anything else, you still don't know kind of what neutrino really got out. And so that's why you get this oscillation. The oscillation is really the quantum mechanical wave that's oscillating. And so I guess linking to electron spin, which is a very quantum mechanical phenomenon, and actually polarization is also, I think reasonably a quantum mechanical phenomenon. It's a good analogy.
Actually, this leads me to one other question from this. If you took a neutrino and anti-neutrino and you shot them at each other, if you could, assuming you could do that, and they collided, would it produce two photons, or would it produce
Trick question. You're asking a trick question because,
ah?
as a matter of fact, we do not know if neutrino is its own antiparticle. That is a spooky mystery that we don't know yet. It's plausible that neutrino is its own antiparticle, or maybe it's not. But I think if you do annihilate them, can they produce two photons? I think they have to. There's nothing else that they can decay into, right?
I mean, everything's conserved.
Yeah.
Gotta be possible.
Yeah, it probably wouldn't like to decay. Like two neutrinos come together, it probably wouldn't want to annihilate into two photons. But if you were to force them to annihilate, then because they have so little mass. Yeah. Oh, okay. It depends on how much energy, right? If they have so much energy, look. It's an energy dependent statement. If you have two neutrino beam with a fantastic amount of energy, it could produce a lot of things. It could produce protons, electrons, and other stuff. But if they don't have a lot of energy, there's not much they can make. So particles of light is probably the only option.
I see. But like, if I collide an electron and positron together, that'll most likely form two like photons, right? Like a beam of light. The light will come out of that.
Yeah, and the reason is because electrons and positrons, or anti-electron, they have something we call the rest mass, or they have mass. So it's the minimal amount of energy that they have, even though they are at rest. This is like the bare bone energy that they have. The neutrino, because their mass is so light, this bare minimum amount of energy is so low that even if you take them at rest, two neutrinos at rest, you annihilate them, there's not much energy left, really. So.
Okay, so it's unclear what would happen if I collided a neutrino and antineutrino. Is that fair to say? Or have people done
Yeah,
this?
yeah, I think that's fair to say. Although the closest thing is we we actually have seen, so in terms of neutrinos and energies, we actually have seen really energetic neutrinos coming from the galaxies, and we
Mhm.
have some of the most fantastic experiments to study them. And this is called the ice cube, and not going to go into details. It's basically using a crap ton of ice in the Antarctica to see if neutrinos will come in and hit one of the, I don't know, one of the one of the water molecule, and create a signal, what they call a Cherenkov light, you know. And this only happens when neutrino has so much energy, fantastic amount of energy, that it's able to create a lots of other stuff. It can create electrons, protons, and whatnot, as to kind of light up that ice, right? And this has happened, and physicists have studied high energy neutrinos hitting other stuff and emitting light and whatnot.
Ah, I see. I see. So you're saying only if it's high enough energy will you get something involving light, most likely.
Yes, yes, yeah, yeah. It needs it because neutrino is so light. Yeah, in order for
Mhm.
you to see something interesting, it's gotta have enough energy.
Yeah, that that makes sense. So we have another audience question, which I'll paraphrase it. Are there gravitational waves from neutrino due to their high numbers and combined momentum?
That is an interesting question. So so let's put it this way. Like in the current era, like with the galaxies and whatnot, uh, we probably don't have enough neutrinos with high enough density to cause any of these fantastical disturbances.
Mhm.
Gravitational waves usually is associated with things like black hole mergers, really massive cataclysmic events in the cosmos, or neutron stars merging together. So you're probably not going to see that. And and then um, in order to see some of these effects, you might want to look at in the earlier universe, when maybe the universe had a bath of neutrinos, right? Um, but then something violent has to have happened to these neutrinos in order to create these cataclysmic disturbances. And I don't believe there are such cataclysmic disturbances. It will only happen if like something dramatic happened, like a phase transition, like a boiling event. Like imagine if the universe is some kind of a bubbling water and it just boils,
Mhm.
kind of phase transitioning out of one universe to the next, then we might
Mhm.
see some gravitational waves. But I'm not aware of any such disturbances related to neutrinos.
I see. That makes sense. Okay, another audience question. Could you mention the search for sterile neutrinos, in quotes? And if we find them, will it maybe point to a more precise standard model formula?
Yeah. So this is something we didn't quite discuss, because we mentioned this kind of spooky phenomenon where a neutrino can kind of spontaneously convert from one another. And for now, we observe that, at least so far experimentally, we observe that there are three types, three types of neutrinos. But then you can kind
Mhm.
of run a little bit of a sanity check. Yeah, because if you let's say you have a neutrino beam, and if there are three possibility, the sum of those three possibility better add up to one. It's either 20% one thing, 70%, and then the rest has to be 10%. So you can measure
Mhm.
each of them independently and to see if they add up to 100%. And there have been
Mhm.
some experiments that says, well, it doesn't quite add up to 100%. Um,
Oh.
so then they were proposed that maybe there could be a fourth spooky neutrino, because you can't see it. That maybe there's a fourth friend of these spooky particles, that it's part of the party. It can come and go, mix them up together. If that was true, that means that we have a missing new particle that we did not anticipate, because the standard model of particle physics dictates that there are 3 and only 3. But if there's one more, then that's a discovery.
So would this fourth one morph into the other 3, or why is it called sterile? Or I'm assuming the fourth one would be the sterile one, right?
Yeah, it's called sterile because we have never directly produced an extra type of neutrino. We have directly probably produced the 3 types. So we know that if there's an extra one, it must not have those ordinary interactions, because otherwise we would have seen them. Yeah. But it's possible that even though we cannot create it, it can be spontaneously converted into from normal neutrinos. Could just like kind of spookily, sneak into a new type of neutrino, and that will be very strange, actually.
I see. So are you saying that the most spectacular neutrino could be the sterile neutrino, actually?
Yes, it could be, but we don't know if we do not even know if it exists yet. And yeah.
Oh god.
Oh yeah, and we also don't know if there's also the mystery whether neutrino is its own antineutrino, and we also don't know if there's a new neutrino, whether it's its own antiparticle. I think all these are all up for speculations, and the experiments are quite difficult because, as you can imagine, these are very spooky particles. They don't really like to be seen, and you have to make billions and billions of them in order to see a few of them. I don't know the exact number. So it's kind of hard to have them show the true nature.
Very scary indeed. I don't know about you, but that keeps me up at night. So I guess this also answers another audience question that asks, can the fourth one be an antineutrino? But I would assume your answer is we simply just don't know.
Yeah, I think neutrino, antineutrino is merely a label. Like we can call neutrino, antineutrino, and antineutrino, neutrino. But the true question is a particle its own antiparticle? I mean, that's an interesting question. And for neutrinos, we don't know. For other particles, of course, we know the answer because we've observed antiprotons, and they have charges. They can't possibly have this. They can't possibly be the same. But neutrino, it doesn't have a charge, so it could be its own antiparticle. So these are all kind of reasons why they are a little spooky. These ghostly particles, they have a little unusual. How do I put this? They have unusual properties that may be not as intuitive to us.
Yeah, that definitely seems like it. Like particles transforming into other particles doesn't seem as intuitive, at least to me. But yet it happens all the time. So we're almost at time. I want to give you a chance to leave the audience with any spooky last minute words of that you want to leave them with.
Yeah, I would say neutrinos is a great spooky lesson. Back in the days before we have all these technology, we had no clue there were neutrinos at all, right? There are 100 billions of them passing us. How could we have known? But I don't exactly remember the how it was discovered. But it was known that in nuclear decay that the sun definitely produced neutrinos, and then just with a lot of stuff in the lab, we were finally able to measure them, and realize that hey, even though they're spooky, they were there. And it's really a lesson that just because we haven't seen something yet doesn't mean that it's really not there. And I guess there's some lessons to be learned for dark matter. It might be a very similar story, or dark matter could be even spookier, but it's just too spooky, I guess, for us to see anything yet. But the neutrino already kind of boggles the imagination. There are all these strange phenomena that if we were just studying physics, might not expect immediately. So lessons from the spooky.
Well said, well said. So actually, two last minute audience questions came in. So I'll rapid fire them to you, and then we can call it a night. So one audience question is, what is the way to distinguish between the two? I assume this person's asking between a neutrino and anti-neutrino. Like, why would you say they're like different labels? They may be the same, but why do we distinguish them as different? Why anti?
Yeah. The thing is, if neutrinos are its own antiparticle, that means that two neutrinos coming together could annihilate. If they're not the same, it means that a neutrino and two neutrinos cannot annihilate, and a neutrino can only annihilate with antineutrino. Yeah. And the way to figure out whether this happens or not is through what we call a neutrinoless double beta decay. This is a very technical term. Basically, we know that in radioactive decay, you have to create a neutrino. How can we not create a neutrino? Is if a radioactive decay kind of decays twice, and then the two neutrinos that got produced in that double decay kind of cancel out each other. So we end up observing a decay, radioactive decay, that has no neutrino whatsoever, but creates two electrons. So scientists have been looking for this for ages. This is probably a Nobel-worthy pursuit. If they do find what we call neutrinoless double beta decay, it means that neutrinos and neutrinos could cancel each other out, and that means a neutrino is its own antiparticle. So, but to definitively prove the other way, I don't know if there's a way yet. But
I guess the question, at least the way I interpreted, was like, how can you know something isn't in the current standard model of physics? How can you tell whether something is an anti-neutrino versus a neutrino?
It's hard because if they are one and the same thing, then they are just, you can label them differently, but they are one and the same thing.
Let me rephrase my question. Why aren't there 6 neutrinos? Because there's by standard model physics, there's 3 neutrinos: the electron, muon, and tau, and there's also the corresponding anti-neutrino things. Why aren't there just 6 neutrinos instead? Like no anti-neutrinos, just 6 different neutrinos.
Oh yeah, this is a little bit of technicality. Like let's say there are 6. Right? But if 3 of them can spontaneously convert from one to another, and they can, let's say you break them into 2 groups, 1, 2, 3, and 4, 5, 6. Yeah. If 1, 2, 3 does everything in the same way as 4, 5, 6, then you might as well call them the same. In order for a particle to distinguish from the antiparticle, something has to be different. For example, the electron and the positron are different because their charge is different. The electron has a negative charge. The positron has a positive charge. So in order for particle and antiparticle to be different, there needs to be some charge. It might be a little bit more abstract, like the neutrino charge, whatever. So really, in order for them to distinguish them, if you look at whether they can annihilate each other, then that will allow you to assign charges to them.
Yeah. Okay. So basically, what you're saying is it's not that like necessarily when they annihilate each other, you'll get 2 photons, or it's not like the exact same as an electron or anti-electron pair, but it's more of that there are these 2 groups of 3 neutrons. Neutrinos, not neutrons. 2 groups of 3 neutrinos, that these groups behave similarly to each other, except you don't have mixing between these 2 groups. It's mixing within the group. Is that correct?
Yeah. You can roughly
Loosely
put it this way.
speaking.
Yeah.
Okay. All right. So I guess that answers that question. Last question, and then we'll cut it off here. Is there something interesting about the left or right-handedness of the neutrino?
Yeah,
This might be a bit more technical, but go for it.
yeah, I'll try to keep it short. I think left-handed versus right-handed is a bit of a technicality. If you really care about, so left-handedness is a property similar to spin. It tells you whether one particle follows the left-hand convention or the right-hand conversion. But it's a little bit artificial because you can always convert a right-handed particle to a left-handed particle by just looking at in a technical way the complex conjugate. You can always look at its antiparticle portion of it, right? So really, it's just a matter of labeling neutrino A versus neutrino B, right? So so once again, it comes down to this fact: is there something that distinguishes between one type versus the other? If there's no meaningful distinction, they can just convert into 1 and 2, then you would argue that they're the same. If there is something like a charge that prevents them from, let's say, annihilating or whatever, then they're distinguishable. So I would say that question is basically the same thing. You can distill it down to the same question. Is neutrino its own antiparticle? Is there basically the question is, look at a neutrino, look at the antineutrino. Is there something that distinguishes the properties of the two? Something that's different. That's the crux. If there is, they're different. If there isn't, then they're the same.
Gotcha. That answers that. So on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah. See you all next week.
Yep. Bye.
Bye bye.